So it's a great pleasure to have Mohammad Hafezi from University of Maryland today here. So Mohammad got his undergrad degree at École Polytechnique in France, and then he got his PhD from physics in Harvard. And he was part of the Joint Quantum Institute at Maryland before actually becoming the faculty there. And he has been working on, because among very few people who do theory and experiment of different quantum properties of light matter. And recently, a lot of quantum information applications, sensing application. He's a fellow of the Sloan Research, and he has been a young investigator with Office of Naval Research. And today he will tell us, I guess, more about topological physics. Thank you, Mohammad.
Yeah. Thanks so much for the introduction and the invitation. I'm gonna use the stick. Hopefully that works. The topic of the colloquium will be about topological photonics and maybe topological electronics towards the end of the talk. It seems to be a very cozy and informal colloquium, so please interrupt me with questions as much as possible. I'm not planning to finish the slides. I have so many of them. Before starting the talk, I would like to also kind of give a broad presentation of what we're doing in my group. And this is a safety hazard. We are working on the theory of quantum simulators, how we can use the new quantum simulators. Usually in many body physics, conductance method theory, we're interested in understanding the system through linear response theory, etc. But now we have quantum simulators. They're small, but we have some access to them. Can we do something that is beyond what we can do with just linear response theory? So this example is that we can actually synthesize topology. I apologize for the bad quality of the figures. I hope that gets improved as we go forward. In post-processing, these are some of the things that we're doing. This is all about theory work. The topic of the talk is this one, topological photonics. I will spend most of my time. And if there is any time left, I would like to also talk about quantum optics of correlated electrons. So quantum optics has been developed for the past 20 years in particular because of quantum information sciences, how to manipulate individual electrons, photons, excitons, etc. The question is that can we use these tools, both theoretical and experimental tools, to manipulate and control now correlated material, not just say single electron or a single spin in a solid state, but let's say superconductor. Can we use light to improve superconductivity? Can you use optical cavities to improve them? And again, I apologize for the quality of the figures. This should be better than this. I see a better version here. Topological photonics, I have to give some background what we mean by photons, what are the building blocks in an optical system or in general an electromagnetic system. I would like to think about them in terms of resonators. So these resonators can be silicon resonators on silicon dioxide, micron scale devices, optical resonators, again, silica, microwave resonators that people make nonlinear microwave resonators to make qubits, for example, or other kind of resonators that you can make, for example, in gallium arsenide, exciton polariton systems that you can actually form these individual bosonic systems and you can couple them. A generic problem in all of them is that these resonators, when we nanofabricate them, they're not identical. Their resonance frequency is different from one qubit to another qubit or from one resonator to another resonator. So most of this talk is about how we can use the idea of topology to basically frequency match these resonators that are not otherwise matched. So can we overcome some of this nanofabrication disorder using the topological ideas? And then the rest of the talk will be how we can actually go beyond that. So for this, let me just very briefly talk about the idea of topology in physics. And again, I apologize to the expert in the audience. Maybe we're topological experts, so don't be offended. This is just a very classical high level. Yes, sir.
Can I ask a very naive question?
Sure.
Why do you want the frequencies of the resonators to be matched?
So any kind of application that you want to do, you want them to be matched. Otherwise, they don't talk to each other. So, for example, I want to make a delay line. I would have many resonators that are coupled to each other. One send an optical signal, and then I want this photonic pulse to spend as much as time possible in this system. But if they are resonance mismatch, the photon comes in and it cannot go. If I want to look at nonlinear properties, if I want to send some photon and then look at the optical nonlinear response of this, again, the interaction time, the time that the photon spends in the system is important. And if I just get, if the resonance mismatch, the photon will be just completely defective. I'll give some specific example how that happens. Or if there are qubits, I want them to talk to each other. If they don't talk to each other, then there won't be any systems as if they're individual. Please ask question. So, topology. Objects with the same topological properties are connected by continuous deformation, no cutting and gluing. So a very classical, very classical version of this is an island. So irrespective, regardless of the shape of this island, as long as we have a piece of land in water, we call it an island. So all islands are topologically the same. So it doesn't matter if it's heart, square, triangular. We always call them an island. But if that piece of land is connected to the mainland through a small piece, regardless of the size of that piece, we call it a peninsula. So we have two different words for different topological systems.
What if there's a lake on the island?
That's not the same. Exactly. So if, unfortunately, we don't have another name for it. That should be an annulus, like an island, maybe. Annual island. Or if you have two, we should have a different. But very good question. So if we had a lake inside, then that should not be called an island. So so can it be useful? So can we make it a little bit more quantitative? Let's say I'm a swimmer. I start from one point over here, and I want to swim around the island. I can go clockwise or counterclockwise around the island, and I would like to come back to the same place. I can do an integer number of time either this way or integer number of time that way. So it's always an integer. And that integer does not depend on how I go around the island. It doesn't depend on the path. It's just always an integer. I was positive if I go clockwise or negative if I go counterclockwise. But if I want to go around the peninsula, that integer is always 0 because I cannot go around the peninsula. So if I somehow relate a physical observable to these winding numbers, then that physical observable will be robust against the perturbation. Okay, so this is very classical. There is no wave function, etc. But you can just map it to the wave function of your photon or wave function of an electron. So if the electronic wave function winds by an integer number, like a vortex, that vorticity you cannot just destroy. Yeah, it has to be some non-trivial deformation to get rid of that vortex. This is a classical version of it. And the first manifestation of this topological physics was in quantum Hal measurement. When you have a two-dimensional electron gas, you have a magnetic field perpendicular to the system. You look at the current and the voltage in the transverse direction, and you measure the Hal resistivity. So usually it's in the same direction. Here it's in the transverse direction. And what people, von Klitz and realized when we did the experiment a long time ago was that if you look at this Hal resistivity as a function of magnetic field, you see the emergence of these plateaus. In a classical system, it should be a line, but then experimentally what was observed is that you have these plateaus. And the location of them is given by a bunch of fundamental constants, H, Planck's constant, E, the charge of the electron, and N as just some integer. And miraculously, regardless of the disorder amount in the system, temperature to some extent, this quantity, this physical observable, just depends on a bunch of fundamental constants and an integer. And now it's actually used as a standard for resistance. So the reason we'll get into this in more details, but on a very semi-classical picture of it is that once I apply a magnetic field, my electrons are charged, so they see the magnetic field, and they do cyclotron motion, very classic. So if they're in the bulk of the system, they can peacefully do their cyclotron motion, and they're localized, so they cannot contribute to the conductance. But again, in this semi-classical picture, if they're close to the edge of the system, then they cannot finish their orbits, and they skip. And we have this skipping orbits, either left or either. And that amounts to the non-zero current in the system. So what matters is actually the presence of this edge, regardless of how what happens in the bulk. I always have this edge, and the current is determined by the presence of the edge of the system. So now, if my bulk is bigger or smaller, it doesn't matter, because that bulk does not contribute to my conductance. Now, if I have a dent on the edge, let's say there's some piece of junk over here, then this electron is supposed to go around that impurity and then contribute. So it doesn't matter about the shape of this edge does not matter. As long as there is an edge, the electron will find its way around. So now the question is that, is it possible to have similar effects for photons? Okay, the same kind of robustness that we have been enjoying in quantum Hall physics, can we have it for photons? And photons don't have a charge, so they react very weakly to the magnetic field. They have magneto-optical properties, but they're usually very, very weak, in particular in the optical domain. So what can we do? Can we simulate these effects and what we did concepts? In particular, why it might be useful is that in a generic photonic system, let's say you have a waveguide or a fiber, it's a nanofabricated fiber. The photons is coming here, and there is some impurity on its way. This impurity can be some nanofabrication disorder on your waveguide, some roughness in your waveguide. So the photon comes with some momentum e to the ikx, and it can couple to the e to the minus ikx very resonantly, because that channel is available. So you can do a coherent scattering and go back. But in these topological systems, if we can manage to tell the photons to see the same effect as the electrons in the previous slide, then the photons should go around the impurity and then continue. Okay. So far what I've told you is very semi-classical single particle physics, and the relevant question is that, okay, this seems to be some solutions to the Maxwell's equation, right? Because photons are obeying Maxwell's equation, and I'm not invoking that there's individual photons or the system is strongly interacting so far. And indeed it is. These are robust solutions of the Maxwell's equation to dielectric fluctuation. So in principle, Maxwell could have come up with these solutions, but it took us a long path to learn about electrons. Electrons have some topological properties. If they are governed by some topological models, and then translate them into photonic systems, and then realize that indeed these solutions also exist for photons. Does that make sense? Now, this is in the absence of yet.
So, yeah, in the bottom photo, so where does this assumption that like this keeps going come from instead of being reflected from the impurity?
Why it doesn't go to the bulk, or why it doesn't get reflected?
Yeah.
I will come back to this, but just the brief answer is that over here, e to the ikx and e to the minus ikx had the same energy. So I could easily scatter into that channel, to the from forward channel to backward channel. Imagine that it's now a chiral system. So e to the ikx has one energy, e to the minus ikx has another energy. Then I cannot scatter into that channel because it has a different energy. So the role of magnetic field is that if my states are going counterclockwise around the system, would have some energy, and if they go counterclockwise, they would have the opposite energy.
What you're saying is a chiral material. Is that what you're saying?
Chiral, yeah, chiral, we have to be careful. Chiral in the condensed matter language, not handedness. because in optics there is also chiral material, etc. Here by chiral I mean I have a state that propagates with one energy, and if I want to propagate backward, it would have a different energy. In that sense, so going back to your question, imagine that I have some magnetic field and I have an electron with orbital angular orbital momentum of L. So if I go this way, it's B dot L. So it has one energy for positive L, it would have the opposite energy for a negative L. Imagine that I have a magnetic field. The states that are going counterclockwise, they would have positive angular momentum, so they would have some energy. The states that are going counterclockwise, they would have the opposite angular momentum, so they should have a different energy. So in the case of integer quantum Hal, that's really the picture. If you have a magnetic field that it differentiates between states that are going clockwise and counterclockwise, and they have a different energy. So if I put something, then I don't get back a scatter. There's a price, energy price. So that's all single particle physics. And now if we add interaction to the system, then not only we would have these topological states, but also we would have topologically ordered material. And that's in the presence of interaction, and that has to do with entanglement, etc., etc. We'll see whether we can talk about this, but most of the talk would be about really this classical topological states that has nothing to do with entanglement. Okay. So that's was a question online? No. So as I said, photons interact very weakly. With magnetic field. So if you want to have some effect, we have to synthesize this effect. It's an actually interesting story, because first we were thinking about this optical photons. Once I was almost done with the work, I realized there is some work by Haldane and Rabu that they actually again looked at the topological properties of photonic systems, but they had looked at the magnetic microwave material, that indeed a magnetic field can have a large magneto-optical effect. But if you want to go beyond other frequencies, you have to really synthesize this magnetic field. So how do we synthesize it? The essential point about that quantum Hal was that you had a magnetic field that would imprint a non-zero phase when electrons would go around the magnetic flux. There's Aron Bohm effect. When I have a magnetic field, electrons go around it, they get a non-zero phase. So if I can simulate the same physics for my photons, if they go around closed loops and acquire a non-zero phase, then they should feel the same Hamiltonian as of an electron going around the magnetic flux. So for this, imagine that I have a two-dimensional array of ring resonators, and the photons are confined in these ring resonators. They go around different plaquettes. These resonators are off resonant. So in practice, the photons spend most of its time over here, and then goes here, but it's off resonant. So it will go to the other one, and will go to the other one. If we engineer this system in such a way that when I go around individual plaquettes, I get a non-zero phase, then I have mimicked the effect of magnet. Okay. How can we do that? It's very simple. Imagine that I have one resonator, as its perimeter is m being an integer, lambda being the resonant wavelength. This is m lambda again, and then m lambda plus lambda over 2. Why lambda over 2 is that if a photon is resonant with this one, it would be anti-resonant with this one. I think that photons over here constructively interfere with themselves. So when the photon comes here, it comes back with a 2 pi m phase. But over here, it will come back with 2 pi m plus pi. So the photon will destructively interfere with itself when it's over here. What's the consequence of that? So let's follow a photon. Photon is happily doing circulation, but there is some scattering region. So it can couple to this waveguide. You can think of these as waveguides or fibers that are evanescently coupled to each other. It comes over here. It won't go back because it would destructively interfere with itself. So it would go over here, spend some time, and then when it wants to go back, it would take the lower path because these are directional couplers. If my photon is coming this way, it can either go this way or continues its way. When it's coming from here, it can either go here or here. So when I'm going from left to right, I take the upper path. When I go from right to left, I take the lower path. If the optical path of the top and bottom are different from each other, then the amount of phase that I get is different. So more specifically, the effective Hamiltonian for these photons that are tunneling from one resonator, let's say it's resonator X and X plus 1, would accompanied by a phase that is non-zero. And this non-zero phase is just the optical path imbalance because of the middle. Sounds good?
Explain again why if it's going from left to right, it must take the upper path and not the lower path.
So because these are directional couplers. So maybe I need apologies to the people online. Imagine that I zoom into the coupling region. This is the resonator. This is the guy. The guy. Photon is coming like this. It can either go like that or like that. It cannot scatter backward. Why? Because I choose this coupling region to be larger than the wavelength of light, such that the momentum of the photon is conserved. So if the momentum of the photon is conserved, it can only go forward.
And photons can only circulate counterclockwise like that.
Correct. Now, if I had chosen the coupling region that was sharp, like this, smaller than the wavelength of light, then I could go 3 ways. That's bad.
Okay. And why can they only circulate
Ah,
counterclockwise?
so here I only consider the ones that are, I pump the system in this direction. If I pump it in the opposite direction, it's a very good question. If I pump it in the opposite direction, all the phases would fit. And that's the key because we have not introduced an external field. And yet, as if we are seeing an effective magnetic field which breaks time reversal symmetry. No, we have not broken time reversal symmetry. Like spin down photons, if you assign a spin down to them, we'll see some magnetic field. The spin up photons would see the opposite magnetic field. It's like a spin orbit interaction. Yeah. Yes.
The purpose of the creation destruction operators there, is this just like a second quantization to show the emergence of the particle at the opposite or at like lattice say n+1?
Correct. Yeah. So if I arrange, any other question? So if I arrange these links in such a way that I can imprint these non-zero phases on the links, then I can have this Hamiltonian, which describes a particle, an electron, hopping on a square lattice with a uniform magnetic field in some Landau. So this Hamiltonian was studied by Hofstadter, and the eigen states, the eigenenergies of this Hamiltonian is given by the famous Hofstadter butterfly. So these are the energies of an electron on a square lattice in the presence of magnetic field. So the magnetic field is characterized by alpha, the strength of the magnetic field, as a function, just goes from 0 to 1 because it's 2 pi alpha. And then these are the energies. It's scaled with the tunneling. So for each amount of magnetic field, you have these magnetic bands that appear like this. This is from, I don't know, 60s or 70s of the famous offset. Sounds good? Okay, so now our photon would see the same effect because it obeys the same Hamiltonian. Because we just simulated the same Hamiltonian for photons. Now, that was the system when we look at the system in an infinite system, a square lattice, infinite square lattice system, or when you put the system on a closed boundary condition like a torus. But if I open the system, if I just, let's say, consider 10 by 10 lattice, then not only I would get these magnetic bands, but I also see the emergence of some states in between these magnetic bands. And those are those edge states that we saw in the quantum Hal slide. In particular, if I look at these states, And this is a 10 by 10 lattice, and I look at the current probability density, look at how photons or electrons are concentrated. You see that they're actually going around the edge of the system, and they're chiral, they're going in one direction. And if I look at these states, they would go in the opposite direction and with the opposite energy. So the ones that have negative energy would go one way, the ones that have positive energy would go the opposite way, which was the answer to your question. And when I have a magnetic field now, these two are having different energies. And what does that mean? It means that now if I put some impurity on its way, if this impurity wants to backscatter my incoming electron or photon, it cannot, because that sister state has a different energy. So instead I should go around and then continue it. Another way to understand it is that electron or photon or whatever particle you want should be single valued. When it goes around some system, it should either be 0 or 1 or 2. The wave function of our particles should be always single valued when we go around the system, when you finish the angular rotation. So if I start to push this state, it cannot change that integerness, that e to the I m theta. So that m cannot change by a fraction. It can either go to m plus 1 or m minus 1. But as long as we don't push too hard, so it jumps by 1, then it has some robustness. So that's basically the intuitive way to understand why these classical states are robust. So now, can we see it in an experiment? If we make these resonators out of silicon or silicon dioxide using these parameters, let's say the radius is typically 10 micron. The photonic wave function or electromagnetic wave function is confined in this waveguide, and it's confined in this waveguide. But if they get close to each other, then they can tunnel, and they can have these kind of junctions. And in particular, again, this is beautiful on my laptop. I don't know why it shows up here like this. The coupling here, you see that they're very large compared to the wavelength of light. So the scale here is 30 micron, and we're operating at 1.5 micron. That's the operating frequency, this telecom frequency. So this is an SEM image of silicon rings on a substrate of silicon dioxide. In a quantum Hall system, you measure conductance, etc. Here, we should measure transmission. You send the photon. If the system has an eigenstate, it would go through the system and it would come out. If the system does not have eigenstate, does not have that frequency available, the photons will be reflected. So by sending a laser field at different frequencies, sweeping the frequency of the incoming light, you can basically probe all those states. In particular, if you park at one of those edge states, and this is the input and this is the output, the photon will come over here, and then it will come over here. We intentionally removed one of the resonators, so this is like the most drastic disorder that you can have. Like one of the resonators is missing, then the photon would not get back scattered. It would go around the impurity and comes out from the other port, and that's what you see in the simulation, and that's what you see in the experiment. This is the initial experiment. 10 years. So, that's the same robustness that we were looking for electrons, and that was this a while ago. Sorry, that was. Then we asked the next question when I was giving this talk was that what is quantized here, right? In quantum Hall, conductance is quantized. What is quantized for photons? They don't have a charge. There is no h bar or e. So what is quantized? One has to go to Laughlin's argument why integer quantum Hall is quantized. And then I don't get into details, but basically for the experts, there is the notion of spectral flow. So here one can actually see the spectral flow by doing some measurement. You can synthesize the flux that you thread in the whole of the system. You can indeed change it from 0 to 2 pi, and then look how the energy states flow as a function of that inserted flux. Then you see it changes by 1, 2, etc., depending on the winding number. One can do something similar to the Haldane model, where the magnetic field is the total magnetic field is 0, but it is staggered. You can synthesize it so we can induce any photon, any magnetic field form. In this case, was uniform. In this case, staggered. And other groups have used it to make topological lasers. So we get the nonlinear properties of the system, or make it reconfigurable by shining light on different parts and then basically creating different magnetic domains. So here would be one domain, here would be another domain, and then the edges will be defined by how they're controlling your system. So this is one platform. There are other platforms that people have explored in the past 10 years, from waveguides coupled to each other, either like this pasta waveguide or just this normal waveguide. In the microwave domain, free space, and you use your mirrors in a smart way such that you can twist light, and it can modulate the system, really great time reversal symmetry. So there is a review that we wrote on a very high level overview of these ideas for non-experts, and then a long review with our colleagues to cover all platforms and all the models that have been implemented until 2019. So now, okay, I'm almost done with my time, but that was the introduction of the talk. So now the real talk was that, can we go beyond Maxwell's equation? And can we have some physics without electronic counterpart? Because what I just described was very similar to the integer quantum Hal edge states. But there is no worry. We're just, I'm glad that we had a bunch of questions. Any other question? Yes.
Your Hamiltonian, is this operators A, do they describe just usual bosonic operators?
Yes. Yes.
And can you introduce some kind of nonlinear parts like A to the fourth, A to the sixth?
A very good question. Indeed, yes, one can introduce them. And a very brief answer to that is that if that nonlinearity is large enough, then you can have fractional quantum Hal states of photons. If you have A to the third, A cube, then you can have, let's say, Fourier state. But that's the parent Hamiltonian of Moritz states for n equals 1 for both. So if you can actually engineer these nonlinearities for photons, then you can look at the topological order states. Okay. So the outline is this, some quantum directions, but I'm not talking about those, like strongly interacting one, but I'm looking at now some nonlinearities in this. So can we use this as a resource? Now this robustness as a resource for pair generation, photon pair generation. And then can we have some quantum optical interface? Can these states of photons that are topological can be strongly coupled to two-level systems? And then most likely we are not going to talk about frequency comb and the second part. So how do you generate single pairs of photons? What you do is that you take a nonlinear material that can be written like this Hamiltonian, but classically it's basically you have some material that has some state, the photon comes, 2 photon pump is absorbed, and then 2 photons are generated. 2 photons are generated at 2 different frequencies, signal and idler for historical reasons. So if this process wants to be resonant, then I should satisfy the energy conservation. So 2 omega p should be equal to omega s plus omega I, and also momentum. The incoming momentum should be equal to the outgoing. In optics, this is called phase matching. These fields should be phase matched. And this is usually an issue when you do it with nonlinear crystals. You have to engineer it to make sure that it's done. If you go to a nanofabricated device, it's even harder, and that's a genetic issue. So you pump the system, and then you generate these photons from lower frequency and higher frequency. One example of it is this ring resonators coupled to each other to increase the time of interaction. You pump the system, and then these photons comes out. Again, this is not perfect. You have resonance mismatch. So this is can be described by an Anderson model of disordered electrons. Photons are hopping. Now here, photons are hopping instead of electrons. But since there is an on-site disorder, if the system is large enough, all the states should be localized. So the manifestation of localization for photons would be that if I look at the joint spectral density of the emitted photon, how strong photons are coming at omega I and omega S in this contour plot, that is, let's say, omega I and omega S. Then if I do the experiment for device number 1 and another device number 2, you see that they're very different from each other. Why? Because this disorder realization changes a lot. So it's a real problem. But what we argued was that this topological physics provides some robustness, provides these channels that are very robust against these on-site perturbations. And indeed, we can make a phase matching that is robust against these frequencies. So that's an experimental realization. So if you do it for a one-dimensional system, see that for 3 devices, when you look at the joint spectral density, it's all over the place because the resonance conditions are satisfied in different parts of the spectrum. But when you pump the system at a frequency that corresponds to the edge of the system, then we see that the photons are coming at the place that we expected them to be. Now, these are experimental data, and this is despite strong disorder. The resonance mismatch was of the order of the tunneling rate between each sun. And our magnetic field was fake. It was not a uniform magnetic field. We synthesized it. It changes from side to side. Nevertheless, it is robust. The only intuitive way to understand it was the single valuedness of the field. So if the photon is making around the edge of the system, it should be single valued. So it should show some robustness, even if the magnetic field is varying over the place. The solutions of the Maxwell's equation should be single valued. Now, one can also do a numerical analysis and show that if you go to larger and larger system, then you can appreciate this robustness even better. So this is some measure of similarity between different devices. When you go to larger and larger system, one-dimensional system goes down and fluctuation increases, but in a two-dimensional system, it stays up. You can also look at the correlation function of these photons to make sure that they're indeed individual pairs of photons. The way that you do it is that you herald the system, meaning that the first photon comes, you make a click in one mode, and then in the other mode, you measure the correlation function. If you have measured one, then in the other mode, you should have only single photon. So this correlation function should be 0 because it kills 2 photons, and then creates 2 photons. So this G2 should be 0. And indeed, the G2 is close to 0 when you look at this heralded one. That proves that it has single photon pairs. Now, this was useful because you generated these pairs of photons, but for some of these quantum information applications, you want the photons to be identical, have the same frequency in time energy or time frequency. You want them to be the same. So you would do the inverse process. Instead of pumping here and generating photons here and here at 2 different frequencies, you want to pump at 2 higher and lower frequencies and generate them in the same band. And that was another experiment that we did to show that you can make individual photons, pairs of photons identical. Let's say for QKD or for boson sampling, you need these pairs of identical photons. And that's indeed possible. Yes.
How many photons are you pumping in, like for these experiments? Like, are you trying to do as close to 2 as possible?
So the goal of our experiment was to show the robustness and compare them side by side, like a trivial system and a topological system. We did not optimize for the yield. One of the issues of any photonic device is the input-output coupling, how much you put in, how much you get out. So our goal was to show that if you take the same material, I don't know, silicon nitride, silicon, lithium niobate, whatever. If you compare this device, the 1D architecture, to this 2D topological architecture, 2D is superior. But if you want to sell it like say to SciQ, then one should really optimize these guys as well. Our claim was that, okay, this is a fair comparison Okay, so that was, this work was led by Sunil Mittal, my former postdoc, who's now at, should update this, is at Northeastern University as an assistant professor. Vikram Ore was a graduate student, graduated, and Elizabeth Goldschmidt, she was our colleague at ARL, and now she's at UIUC. Okay, so I have 5 minutes, right? According to the missed clock.
I'll take a question actually
Yes.
before you read this.
Yes,
So does this size matter?
Size of
So
this.
if you make it like 100 by 100, 10 by
very
10.
good. Yeah. So one of the important application is the footprint. We are going from 1D to 2D. So okay, what did you achieve here? Now you're taking more space. We don't need to have a square. We should not have done the experiment with square. I don't know why we did that. You can just do it for a strip like this. So as long as the system size is bigger than the edge width, here it's given by the magnetic length, then this forward states and backward states cannot couple to each other. So I don't really need to have this 10 by 10. If it was 10 by 4, that's enough. Our magnetic length usually is just one side. Now, if you want to sell it, then just take the word. Okay, so I will then just do a brief review of what I wanted to talk about. That was ring resonator system, nice platform. We did this single photon generation, pair photon generation. We wanted to now understand how these edge states can be coupled to two-level systems strongly. And for that, we had to change our architecture from going to ring resonators to photonic crystals. Because one can embed quantum dots or other kinds of bright emitters, two-level systems in the optical domain in photonic crystals, but not in ring resonators. For technical reasons, and we can chat about that. So how can I take a crystal and make it topological? This was inspired by topological insulator literature, same in electronic systems. You can also have lattices that are topological, that have topological properties. What you do is that you start with a system that has some symmetry. In this case, it's this C6 symmetry. You have a honeycomb, and then you start deforming the system in different ways. So in one side, we take these are holes in gallium arsenide slab. You can shrink these guys and open a band gap. You can expand these guys and open a band gap. But now what is interesting is that if you look at the Maxwell's solution for these guys, you can look at electric field and how many number of times it winds, like a wave function of an electron and a hydrogen atom. Is it S wave, P wave, D wave, etc. And if you manage to do this deformation such that these are P-like and these are D-like, but for this one, they're the opposite. So the upper ones are D-like and the bottom ones are D-like. Then you have inverted the bands. And it's guaranteed that once you invert this band on both sides, on each side, then you would have helical edge states in contrast to the chiral states that with one polarization, they go one way, with the opposite polarization, they go the opposite way. So that's what they call helical. And again, this is a SEM image. These are holes here, holes here. These are gratings. So if you put a two-level system that emits light with this polarization, it should come out over here. If it comes with this one, it should come out over here. And then indeed, we experimentally observe that they come out at different ports. Different polarization come from different ports. And this is like a Lego. So as long as you don't break your bricks and then make these topological regions distinct, you can actually have an edge state that just go around at the interface of these two distinct topological regions, as long as you don't break the crystalline order of your system. So yeah, so the photon will actually follow these topological bands. So we can play with that topological table. And Okay, so that was this part. You can make all kinds of resonators. As I said, these are Lego. So you can make a triangle, you can make stars.
How do you know, what is the insight in choosing those things?
I just have to make sure that I don't. So my unit cell is this. Now, as long as I make sure that the interface is respected, so I can do any 120 degree bend.
And the directional coupler argument, does it still hold up there, or?
That's a good question. That's kind of because it's good over here, it's good over here. At the boundary, you may break some of them. We actually did simulation and we realized that they're preserved. And there are still theory papers that I'm figuring out why it works so well. It actually works better than one expects, because you may think that I'm breaking the symmetry of this spin, but you don't. Yeah. No. Because this argument is not a crystalline argument. It's a continuum argument. That's an excellent question. And why it's preserved? A bunch of theories. I kind of convinced myself somehow. Okay, that as long as this deformation preserves some symmetry, they're fine. If it's completely destroyed, no, you will flip the spin and it's not protected. But for these bends, it is protected. So I'm just making the same bend. It's just different shapes, but that's fine. If you buy that 120 degrees fine or 60 degrees fine. Okay, so then the last part of the talk was using this. I acknowledge the people who are involved in this part. It was a collaboration with my colleague Ido Wax at JQI, and the lead graduate student who again graduated was Savyasai Chibari. So another application of this is this topological frequency comb. A frequency comb is like a ruler for time and frequency. We have a ruler, it has equidistant bars such that we can measure space. For time, you should have some pulses that are the distance by specific, by equidistant in time, or if you take the Fourier transform of this, you get equidistant in frequency. And these are useful because I want to measure time and frequency, that's the case. So, and you want them to have as small as possible, so you want to miniaturize them. So there is a lot of work how to do it in silicon nitride, etc. And the one problem is that it has low efficiency, and the other one is lack of tunability. So it's not really the problem of disorder, etc., that I advertised in the beginning, because here we are dealing with just one resonator. It turns out that in topology, you have actually more than just robustness to these things. And yeah, so the short answer is that indeed you get, for a single ring, you get some 5% efficiency, meaning that how much power you put and what kind of comb you generated. This was a joke. Time. This is the Turing pattern. At some point, you will have Turing pattern. This is Turing came up with some a nonlinear diffusion equation to describe how patterns are generated in the biological system. I don't know whether it's actually relevant in real life or not. But so it happens like this Turing pattern happened over here. And long story short,
What is the unit of mu?
I'm sorry.
What is the unit of mu?
Mu is unitless. I have a resonator. This longitudinal mode photon can wind by 1, 2, 3, 4, etc. When you solve the Maxwell's equation in the cylindrical coordinate, you have e to the I m theta. That m is this one. So you can again make this topological system to create your comb, and these are in the form of solitons, but even better, they're robust. So if some of your resonators are missing, soliton comes and it sees this missing resonator, it goes around it and it comes out. And what we realize is that the efficiency of these combs are 50%, more than 50%. We don't understand the real theory behind it. It's based on all numerical simulation. And that's an ongoing work. Maybe there is some phenomenological work that one could do to understand this very tiny part of the phase diagram, the strength of the pump and the frequency, to see why we get these solid. That's it. So let me summarize. I hope that I kind of am motivated that this topological photonics is like a new design principle. So whatever you do, you want to have a laser, I don't know, quantum source of light, doing cavity QDs, slow light, tapers we didn't talk about, antennas, frequency cone. Can I do them in the topological fashion that are more robust or more efficient? And I have to keep in mind that I have to compare them with one-trivial structures with same parameter. Same material, same parameter, not just show that, okay, topological is possible. That's good. But if we are serious, we have to show that there have real advantage. I did not talk about strong interaction. You can put strong interaction using Rydberg atoms, or you can just go to the microwave domain where you have qubits. And then the question is whether you can make topological like fractional quantum Hall states and how we can measure them. That's also another question. So with that, thank you very much for your attention and questions.
Thanks so much. Any questions?
Can you do any kind of computation with these systems?
Classical or quantum?
Any, like, let's say classical.
There is this idea of optical computation. I wonder whether they suffer from, and they want to do it like on chip, of course. I wonder whether this is useful. No, I've not thought of it. But the quantum one, the complexities of making these states is an ongoing field of research. Like, for example, this topological one, they are these fractional quantum Hall states are the states that we cannot make them easily with the finite depth circuit, system depth circuit, etc.
Well, what does
Understanding and
electron-electron interaction mean here when you say fractional?
What's that?
What does electron-electron interaction mean in this language? Is it photon, but that's electron-electron, right?
Well, photon. So,
Yes, it's photon.
so like this question was that you have this tunneling, and then you had some phase like that.
Right.
But now I have to have some interaction. And for photons, actually, it turns out that just on-site interaction is good, is enough. Let's say for n equals 1/2 for photons, this is a Laughlin state n equals 1/2, and it's gapped, and it's unique.
But the more read fraction.
No, the more rate would be cubed.
Oh, the cube. I see.
Yeah. So this one will be at this filling.
That's the fraction.
Yeah.
Right, got it.
And then this is the lattice version of this one. And these are bosons, so this is a legit waveform.
And if you see fraction, you just change your platform. That's the same experiment.
Well, yes. I mean, of course, adding this interaction in the scalable way is a trillion-dollar question. But yes, from a theoretical standpoint, yes, just add an interaction.
So is there something with these, like this photonics, these ring resonators? Do you think it's possible to do this in like mechanical resonators?
Oh, yeah, very good. Indeed, there is a group at ETH Zurich that they have done a number of works looking at topological properties of mechanical systems. Excellent question, because I was talking about Maxwell's equation. So any kind of second order equation you can take and make it topological for these states, for this fractional, etc. I don't know whether that
So
makes
does the
any
coherence
sense.
matter then? The coherence of the
Coherence
topology
matters,
factor
of course.
that.
As long as it can be described by the wave equation, then it's good.
I see.
But if your mechanical wave cannot travel around your system size, around the length of the system, then of course you want. The same with photons. If my loss was too high, such that the photon could not travel around the edge of the system, then I would not have those.
Please, that makes me ask another question. What's like the quality factor of the ring resonator?
So there are two quality factors. There was the loss, and there was how strongly they're coupled to each other.
Right.
So here we are talking about 10K. Q is about 10K. The loss. And then the extrinsic one, coupling, was 2-3 times that large.
Any other question?
Did you try to make some kind of bosonic version of Majorana fermions?
Very good. Another very good question. Indeed, actually, I thought about it, and then I saw a paper. And then I convinced myself that's not possible. I saw a paper and I said, no, they actually wrote it in a collectively correct way. And it's written Majorana-like. So the story is a little bit complicated, but it's just it's not that complicated. So if you have this guy, you can have Hamiltonians like this or photons. It's like a P-wave pair, right? And then you can also have strong interactions such that you can have either 0 or 1 photon. Then formally you can have the same Hamiltonian as k-types, but these are bosons, hardcore bosons, which are basically spins, which are basically so you can make Majorana fermions after Jordan-Wigner transformation, but they are not robust because any local disorder here in the fermionic picture would be a non-local disorder, right? Because Jordan-Wigner, the whole point is Jordan-Wigner transformation.
So I guess I don't know if other people hear us on Zoom, but if there's any question on Zoom, maybe we can take those. Okay, I guess there's none over there. There's none here. And let's thank Mohammed again. And